SwayamPrabha. Digital India. Educated India.
The idea is that within those applications that I showed you, not only you can deal with micromechanics of composites where you fully resolve those composites, but you can also deal with situations like carbon nanotubes where they're happening in very small scales, and you can do it in two approaches. So you can combine all these phase field technologies with micromechanics, any sort of micromechanics that you're interested in. So it could be mean field homogenization in that case at the beginning, but then also this sort of RBEs. And we have not extended that to fracture. The idea was to, it's a complicated, when you're dealing with RBEs and fracture is another story. There's a separation of the scales that you need to be aware of and so on. But the idea was more, can we have a RBE-informed micromechanical model that we can then run these kind of large-scale calculations? That was the motivation. Okay, today I want to get into fatigue. This is the content of the day. This is a very much ongoing area in the phase field fracture community. So the first paper was, I think, 2019, 2020. There was one from the US, from the group of Bourdain. And then I think it was the group of, it's UT Austin, the group in UT Austin. And then there's another one from Laura De Laurentiis at ETH that came in 2020, which is the approach that most people seem to be using. So it's not that long ago, again, 2020. And most of the most relevant papers, I think, have appeared in a few years from now. So there's still a lot of papers coming out. It is, as I said, an ongoing topic of research. I don't think the models are as mature as in other areas, but we'll still go through it because it's quite an exciting area of research. Of course, many failures happen due to cyclic loading, due to fatigue. A lot of people are interested in fatigue, scientists and engineers. It's kind of one of the, a friend of mine used to say that hydrogen embitterment was the ultimate challenge in solid mechanics because it was so difficult to understand and so complex problem, and we didn't crack it yet. I think fatigue is probably also the same thing. Fatigue is such a complicated problem. We still very much use empirical tools to predict what's going to happen with structures subjected to cyclic loading. So it would be good to achieve some scientific breakthroughs in there. And I think phase field has some potential in that regard, but it's still a very much ongoing topic of research. So I'll tell you a little bit of how it works, and then I'll tell you what I think are the challenges that we face in this area, some of which are of computational nature. So yeah, this is the plan for today, and then we'll see some hydrogen embitterment until we reach the time. So a reminder of what we discussed in the very first lecture on Monday. So there's basically various regimes in fatigue. So we have a first regime where everything is very macrostructural dominated, where most of the time you spend nucleating a crack. This is the most challenging regime in terms of understanding and prediction. Then we have a regime where you already have a macroscopic crack, and that macroscopic crack is growing. And it's growing following Paris law. And then you find the final regime where basically your crack is close enough to the final crack size driven by static fracture, and so that it will just grow very fast. So how to characterize things in the regime B? This is the Paris law. This is what everyone uses. It's still a bit empirical. You have a C and an M parameter that you need to fit to experiments. So it will be great to reduce that empiricism. It will be great to actually figure out what this C and this M mean from a bit more first principles, more mechanics. And then the other regime is regime A, this first regime, first stage, where basically you're nucleating a crack. This is very macrostructurally dominated, and normally we evaluate that regime with SN curves. So we run this kind of experiments where most of the time we're basically nucleating a crack, so we're just alternating a uniaxial tension test with cyclic loading until we measure the failure of the sample. And again, we get a lot of scattering there, but we get these kind of curves that are used in fatigue design. So these are the two ingredients, and I guess the question is, how does phase field fatigue fit into those ingredients? The idea is relatively simple. So basically you add a fatigue degradation function that reduces your fracture toughness. And again, there's been other groups following other approaches. This is the one proposed by the group of Laura De Laurentiis. So this is a paper by Pietro Carrara and co-workers in 2020. As you say, depending on how you degrade your fracture toughness, whether you degrade it in the strong form or in the weak form, you get a different strong form because there's a gradient term that comes along with it. I can send you some notes if you're interested in. So here, for simplicity, I'm just going to show this version. This is actually not exactly what they did. They degraded in the weak form. It's a bit philosophical whether you want to degrade things in the strong form or in the weak form, because, well, you could argue that you could degrade things in the energy balance point of view, like, from the Griffiths perspective, you are fatigue, the cyclic damage is changing your material. You're making your material with a lower fracture energy. Or you could just think of the phase field, the phase field as a variational approach, and then you need to degrade things in the weak form. So anyway, I'm going to forget about this extra gradient term. It's anyway, it's small and only matters near the interface. So I'm going to focus on I'm just going to make it simple by expressing things like this. So the idea is that you have a fatigue degradation function that accumulates with the number of cycles and degrades your fracture energy. That is the idea. So you can use the same phase field. It's something that basically accumulates and makes your material less resistant to crack growth. So what to do about this? Okay, what choices do you need to make? Well, you need to make a decision on what is this history variable. So you have a function. So I guess the two choices that you make is what is the shape of this fatigue degradation function, and what is this what is this history variable? What is what you're accumulating over time? So the history variable you can accumulate over time like this, and this alpha variable, what makes more sense is to pick the strain energy density, right? Because I mean, you have a choice. You can pick whatever you want. You can pick the stresses. You can pick strains. It's completely up to you. Anything that accumulates over cycles you can pick. But I think the strain energy density seems to be the more consistent approach when it comes to making things consistent with the framework of phase field, right? It's all an energetic approach. We believe that the strain energy is what drives the cracks. So why not accumulate the strain energy density? So there's not much choice here, I would say, if you want to keep it along the same lines. Then there is a choice on the fatigue degradation function. And then what they proposed a few degradation functions, but the simplest one was this one, this kind of asymptotic approach. And here there's a parameter, this alpha 0, which is a material property. And here, I mean, again, as I said, this field is not as mature as it could be. It's the beginning of this area, this discipline or subdiscipline. So we have this alpha 0, which, I mean, is not as beautiful as toughness or strength. We don't have tables of alpha 0s out there. That being said, I mean, the physical meaning is clear. It tells you, for a given cyclic load, how much your material will damage. So some materials will be very susceptible to cyclic loading, others will be less. So that was quantified through alpha 0. And I mean, at the end of the day, the good thing about this model is that you rely purely on one parameter. So with one fatigue experiment, in theory, you feed your alpha 0, and you pray that it will work for other conditions. That is basically the idea. Yeah. This is the Heaviside function. Sorry, this is the Heaviside function. But you don't worry. I'm not gonna. We don't have really time to go through every detail. Feel free to ask questions, of course. But I don't want to go. I just want you to get a big picture, kind of the things. But of course, everything is detailed in the papers as well.
So how do we get this alpha function from experiments?
Yeah. So that's a good point. So there's two choices that you're actually making. It's not only one parameter. You are deciding well, there are three choices. Your driving force, which again we're going to pick the strain energy density. So we don't make much of a choice there. You have a parameter alpha 0, and then you have a function they propose multiple functions. They just, again, you will have to calibrate to an experiment. So I think it is true the field is still a little bit empirical. It would be great to have a function that somehow we connect to something, like with hydrogen we discussed yesterday, how you can do atomistics to define that function. It would be nice to connect a bit more the links, but still fatigue is a very empirical field in general. So I'll tell you a little bit of how we came up with other functions and what we found. But yeah, for the time being, you make two choices, your function and your alpha 0, and these have to be somehow fitted to an experiment.
Can we think of units of this alpha bar? Are it dimensionless?
This is dimensionless. No, this has units. I've forgotten what units we have here. So I guess alpha, so this is, I guess, same as the strain energy density, right? So I guess megapascals. So then the good thing about it, so the bad thing about it is, we have to make some choices. These choices are qualitatively in the right direction, but we depend on some values that we need to fit to an experiment. But the good thing is that, these are results from their paper. When you run these calculations, you predict as an output of the model, not as an input. And before this, I mean, there was some work done with cohesive sum elements, but other than that, all the models that we had there for fatigue, they will normally, you do the test, you feed the data with that test, and then the model will only reproduce the test, basically. You will not be able to reproduce tests without any experiment. But here you can see that, without any experiment, you capture both SN curves. So this is kind of load versus number of cycles to failure, both SN curve type of behavior and Paris law type of behavior. And again, the Paris law comes out of the model. So remember, Paris law has this C and this M. I don't put any C and M in this model. I just run my simulation. The same model that I use for an SN curve. You can see here, this is for a load of 10 newtons. So it goes like this, and eventually you fail. So it's exactly, it's not only Paris law, it's the entire regime. You can see that we capture the entire regime with this model. So it looks promising. Again, there's some things to polish, but it looks quite promising because, Paris law is a lot of the people use Paris law, and because, well, you need to do an experiment, but that's okay. We can run an experiment. But Paris law is only appropriate of a certain regime. So there's a danger that you're applying Paris law here, where it wouldn't make sense. There's a danger where you're applying Paris law here, where again, it wouldn't make sense. So this model not only reproduces Paris law, but it's also able to capture the whole experiment from the delta K threshold all the way to the complete failure. You can see it in all these cases for different load ratios. So it's quite promising. You can get S and curves and Paris law out of the model. It's not an input to the model, it's an output of the model. This is the main difference with other existing models. And then, so we started working into this, and this was work that was done by my student Aligesa Golamar, that I co-supervised with Christian Njorsson in Denmark. Aligesa was funded as an industrial PhD student, so it was funded by a company, Vattenfall, who are looking to extend the lifetime of offshore wind turbines. They operate and manage the oldest offshore wind farm in the world, that is called Hornsrud 1, it's in Denmark. And these offshore wind farms, I'll talk a bit more about that when we talk about multi-physics problems. But these offshore wind farms, they're supposed to last only 25 years. And the oldest one in the world, this Hornsrud 1, is 24 years old now. So they very soon need to make a decision on whether to extend it or not. And because fatigue is so empirical, because this 25-year decision was something, you will see a bit crude. So they were hoping to improve those with some mechanistic predictions, and they funded this PhD studentship. But he had a very practical mindset, and he said, I'm interested in publishing papers, but I'm also interested in coming up with something that is useful. So then he realized of multiple challenges. The first one he realized is that, this is okay because this is all very qualitative, but when you try to fit experiments, this model was not good enough for him. He needed a bit more flexibility. So he changed a little bit his approach. Basically, he changed the way we accumulate this alpha, this increment in alpha, and he came up with this equation. He said, this is what I need to capture experiments. So the idea is that you have now various ingredients that I will discuss, but basically you accumulate your cycling variable as a function of these variables. This is the Heaviside function. So there's a term that accounts for the load ratio. There's an exponent n, and then this alpha 0. So basically we have, this is the load ratio that you apply. So we have an extra parameter. That's the price to pay. You add an extra parameter. But he felt that he needed to add that extra parameter, otherwise he wouldn't be able to capture experiments. So first things first, just to make some definitions. So when you have a peak, or whatever variable it is, normally we talk about strength and density, what you're accumulating. So it's maximum, of course, here, is minimum here at the bottom. So this is what we call sigma alpha max. This is the alpha max, and remember the usual notation. This is sigma mean, this is sigma max, this is the range, this is the amplitude, this is the mean stress. So this is the variable. So that's an output of the model. We run your experiment, and locally, your numerical experiment, and locally you have an alpha max. But what is important was to define this n term that was not present there. We have the alpha 0, but we didn't have the n. And with the n, he could see that he could take any slope of the SN curve. So the model that Laura's group proposed was good, but it didn't allow you to capture every SN curve, at least with that fatigue degradation function. So he was able to capture this SN curve, and he was also able to find that there was a relationship between this SN curve and the Paris law behavior. So he could relate them so the parameter m in the Paris law relationship could be related to this n behavior, which you can show theoretically for linear elastic materials. I'll discuss that later. Then he saw that there was an R ratio effect that you could not capture with the previous model. So he said we need to include something here. And there's a lot of people working on semi-empirical relationships. These ones are the most famous one, the Walker relationship or the Smith-Watson-Tupper relationships, whereby they can capture the effect of the load ratio. So he did that as well, and you can see here comparison with experiments. So the open symbols are the experiments. These are for two different materials, experiments conducted with multiple load ratios. And the model seems to be in very good agreement with the experiment. So he was, being an industrial PhD student, he was very interested in making sure things fit, and he was quite happy when he saw this kind of results.
Quick question, so the degradation, is it as a function of cycles? So you upgrade at the end of the cycle, or is it happening also inside the cycle?
Yes, very good question. We'll discuss a bit later on. So initially we solve maybe 10 increments per cycle, so you solve the entire cycle. But it's true that you only accumulate damage in the tension part, and this is something that we'll discuss a bit in a minute, because the different splits depending on which split you accumulate. So Griffith will accumulate in the tension and compressive part. But of course, in reality, we only accumulate in tension. So you have to do some tricks in there, and at the end, you end up basically accumulating only in the tensile part, which allows you to kind of jump over cycles because you only care about alpha max, basically. You only care about alpha max. This is something that becomes very important a bit later on, because one of the challenges that we have is the computational cost. We're running cycle by cycle calculations. So if we don't need to do the full cycle, if we have just the peak cycle, then you can jump over cycles. This is a very good point. So just to finish, the last ingredient here was the endurance limit. So he wanted to incorporate the endurance limit. This is widely used by engineers, sometimes when you can oversize things to make sure that you're below the endurance limit. So you have this heavy sand function. And you have this extra parameter, alpha E, but it comes from the experiments. Each material we have tabulated data of alpha E. So it is an extra parameter, but it's again a physical parameter. We know what is the threshold for. You can see the relationship here, by the way. This is the definition. So I wouldn't say it's an extra parameter in the sense that, the endurance limit of a material, we have tabulated data for each material, so that we know very well. So this we know before we run the simulations. Again, just connecting a little bit with the seminar yesterday. Ideally, we want models where we know all the parameters before we run any simulation. In fatigue, I don't think we're there yet. This parameter, yes, the endurance limit, we have tabulated data there. But this N, well, you can get from S-N curve, so it's not too bad. Alpha 0, we need to fit. So we're not yet there. But then again, here you can see that we can capture quite well. And this is, by the way, simulations for different stress concentrators. And you can see that for different stress concentrators, the model seems to be in good agreement. So the same material, but you change the shape of your component, and you see that you are in good agreement. Okay, the other challenge is related to this question that I just got from Anand. So what do you do about the strain energy split? So if you accumulate, so we said this alpha is the strain energy density. Griffith doesn't understand tension and compression. Remember, if you think of the uniaxial 1D case, is something like this, right? So if you are under tension, these two are positive. If you're under compression, these two are negative. They cancel each other, so you get a positive term of the strain energy density. Just thinking 1D. So that's a problem because you will accumulate damage in both loading and unloading, and we know that in reality we don't typically accumulate damage under unloading. And this is what you, yeah.
So what if it's a tension cycle?
Then you're safe. Then you're fine. No, because you're accumulating. Oh, sorry. So I should clarify. So the load ratio, if it's equal to -1, then is when you have a full tension compression cycle. If it's positive, and actually we don't really model that much R to the -1 because there's a lot of crack closure effects and other things that are a bit nasty and not really very well understood. So we try to stay away a little bit from that. So we normally look at R 0.1 or larger. But even then, you will be accumulating because this variable is just growing. You're accumulating in both tension and compression, or loading and unloading, I would say, in a way. So you can see it here. This is the example. So this is this is R to the -1. Okay, so it is true. It's very sensitive to the load ratio. It's quite sensitive to the load ratio. This is R to the -1 that I remember. So this is, by the way, for the three splits that you know. The isotropic is the no split. So this is a standard Griffith. Volumetric deviatoric is the one of Amor. And then the spectral is the one of Christian Mie. This we discussed before. You can see crack extension in that square plate that we discussed the other day. And you can see crack extension versus number of cycles. Some of the paper from the Laura de Lorenz's group and our paper. This was a paper we published in 2020, the quasi-Newton one. And you can see that we get a relatively good agreement with Laura de Lorenz's model. We actually get this one to converge because we use the hybrid approach. And the other thing that we see here is that you get a very different answer depending which split you take because of this, what you do when you're under compression. And this is R to the -1. Yeah. So what you do under compression affects, of course, how much you accumulate. So we concluded that for us, the only approach that seemed sensible was to use this no tension split. This is initially developed from masonry materials, but is the way that allows you to basically accumulate damage only under tension. So if you look at a bar subjected to R to the -1, again, if you increase your R, then problems go away. But for R to the -1, you can see here that this is your cycle. So you can see that this is the total strain energy density. This is the positive part, the tensile part. This is the negative part. And you can see that so you can see, first of all, is you load. This is one full cycle, right? You can see 0 point cycles, 1 cycle, 1 point cycle, 2 cycles. First cycle, you're accumulating your strain energy density in both, so in both the upper part and the lower part. And you can see that basically we care about the red one, right? We care about the tensile strain energy density. This is the driving force for fracture. We're going to take alpha equal to this plus. So you can see that you're accumulating a little bit in the upper cycle, but also in the valley, not only in the peak, but also in the valley. And the only one that does this consistently is the no tension split. So we decided to stick to the no tension split. And here you can see that in the no tension split, you're accumulating only when you're going up, and then you're not doing anything in the second part of the cycle. So if we go here, and this is important because it relates to the question that Anna was saying. So we want to accumulate here, we don't want to accumulate here. And the no tension cycle is the only one that accumulates damage only here. And the good thing about this is that if we accumulate damage only here, if we know the damage we accumulated here, we also know the damage we accumulate on the way back. So that's the only thing we care about, the alpha max. So this is the second challenge. You need to pick a strain energy split that accounts properly for this decomposition between compression and tension. And it seems that the no tension split is the only one that can handle that. Otherwise, you're going to get this type of behavior where you get very different responses depending on which strain energy split you use. The other aspect is the calculation time. So being able to run fatigue calculations cycle by cycle is very powerful from a predictive perspective, because very often, of course, we do our experiments assuming a constant stress amplitude, but in reality we don't have a constant stress amplitude, right? So we work with people, for example, in batteries where they charge electric cars, and they do have a history of loading, but every user charges their electric car in a different way, so the battery is exposed to a completely different cycling history. So that's a problem. Normally in fatigue, the way engineers get around it is by assuming a linear elasticity, superposition, and you basically kind of do Miner's rule, so you accumulate damage here and there, and some sort of accumulation of damage based on superposition. That's okay. I mean, it has worked for many years, and some things are falling down, but not everything is falling down. But there are many situations where this doesn't work out very well. If you have an overload, or for example, when you have other phenomena happen like corrosion fatigue and so on and so forth. So being able to actually handle any arbitrary loading history, that's very powerful. But of course, if you need to run millions of we've been discussing already phase field, you need to resolve the fracture process zone, you need to resolve that length scale in there, so you need a fine mesh. If you need to do that, and in addition, you need to do millions of cycles, that's going to come at a cost, of course. Even if you only do 2 increments per cycle because you only look at the peak load, it still is going to come at a cost. So there's various ways in what people have tried to accelerate this. We're working on a paper now comparing the various ways. This is a very much ongoing field, so there's a lot of, in the past 2 years, there have been, 10, 15 groups presenting acceleration schemes for phase field fatigue. So it's very much on the computational side of things. There's a paper by Laura De Laurentiis recently comparing various approaches. Our take to this was using first quasi-Newton approach, this BFGS monolithic. This was discussed the other day. When you compare particularly to single stagger schemes, these are far more efficient. You can see we get the right result with 4 increments per cycle versus staggered approaches where you, even with 500, this is single pass, 500 increments per cycle, you're approaching the good solution, but you're not even there. So that's, that can be a deal breaker. And every time you see single pass stagger results in fatigue, it's always a bit of you need to take it with a pinch of salt because it's quite complicated. The other approach is this constant load accumulation. So since we only care about the tensile part, we may not have to resolve the entire cycle. So this is in relation to the question that Anna was saying, right? So we don't have to go to tension, compression, tension, compression. You could in principle just move in this line over here. You just need to know what is the load that you're applying. So you can see here the different approaches, and then you get exactly the same basically. So this is the original formulation, this is this constant load accumulation. At the end of the day, you accumulate the same alpha with the number of cycles. You just basically need to think of your alpha max. And then you can combine this with something that is called cycle jump. This is used quite a lot in Cuisisome elements when you do fatigue. So if you imagine that you're modeling millions of cycles, 20 million cycles, then cycle 1,234 is likely going to be quite similar to 1,235. You're probably going to accumulate the same amount of damage. So maybe you don't need to do every cycle. You can do 1 cycle every 10, 1 cycle every 100, and so on and so forth. So that's another idea, this kind of cycle jump. And you need to be careful, of course, not to jump too fast. So there's always, there's some people now coming out with some sort of error schemes that will tell you how far you're deviating. And then the other approach that we took was this kind of modified Newton, where maybe if the cycles are not changing too much, maybe you're not really changing things too much. Maybe you don't need to build the stiffness matrix every time. Maybe you could just solve with your original stiffness matrix and build every X number of cycles. But I guess what I want to say at this time is that with the combination of 2 or 3 of these acceleration schemes, we are getting to calculation times that become sensible. So what you see here is a bar, is a 3D bar that is quite finely meshed. You can see the mesh. So the mesh is quite fine everywhere. They has a tilted crack, and it's a uniaxial tension, but it's a tilted crack, so it's going to behave in some sort of mixed mode condition. And because we don't know, how the crack is going to behave, we use a very fine mesh. So we use more than 3 million degrees of freedom. And this was running our Julia code, by the way. So 3 million degrees of freedom. As you can see, the crack propagates in a funny way. And we can do 600,000 cycles with a direct solver and using a cycle jump of 4 cycles, which is very small. We could have probably done 40 and we'll probably get the same result. So in fact, this precise model, we solved it later on over a bit of a longer time in the supercomputer, and we could do 1.5 million cycles, I think. So, I mean, it is computationally expensive, but if you can do 1.5 million cycles with 3 million degrees of freedom, full 3D simulation, with direct solver and not being very ambitious on the cycle jump, I think you're getting there. I mean, the most challenging engineering problems will be 20 million cycles. Maybe in railway infrastructure it will be maybe 100 million cycles, but you are getting already to the scales that matter. So I would say, computation times are an issue, and there's a lot of work going on in the computational mechanics community to accelerate this. But I think that we are getting to a point where we can finally do, the time scales, the large scale problems that we're interested in.
How much time it take to?
This took the 600,000 took 5-6 days in the supercomputer in Denmark. The other one was the 1.5 million cycles. I think it took a couple of weeks. So it is heavy stuff. I mean, industry wants things that they can run overnight, not having to wait 1.5 weeks. But I think my point is that bringing an optimist knows we are getting there to a point that we can finally do those things. Yeah.
What might be the possibilities of reducing the competition?
So what can one do? Yeah. So the cycle jumping is a good idea because when you're running millions and millions of cycles, it doesn't make any sense. You for sure cycle number 200,000, 2022, 325 is going to be equal to 326. The accumulation of damage is going to be very similar. So for sure, the cycle jump, I think one could be more aggressive. The problem with cycle jumping is that you don't know. If you say, I'm going to do 1 cycle every 1,000, then, well, maybe you skip some things. And the other thing is that, one of the beauties of phase field is that you can handle, so if you're just going to deal with linear elastic problems where you can apply some sort of superposition and cycle jumping, that you may as well do it with, conventional empirical fatigue design rules. The beauty of this is that you can couple this with fatigue, with corrosion, with plasticity, with history-dependent problems that are much more complicated, hydrogen. But then, can you do those kind of jumping when you have variables that are history-dependent and you need to transport with you? That's a good question. We tried doing some time ago some sort of machine learning as well, some sort of imaging technique to accelerate the crack and move the fields along. But the student had graduated and we didn't pursue it anymore. You can use iterative solvers. Again, when the problem is more linear, more simple, they work very nicely if you find a good preconditioner. But when it becomes when you want to do the exciting stuff, the corrosion and fatigue, the plasticity and fatigue, then it becomes again complicated to handle those. So I think, I guess the good news is that there's lots of things you can do. People are also working adaptive mesh refinement. There's so many other things that one can do. But those things seem to work well for the problems where are easier, which is linear elastic and so on. For the difficult problems, you kind of need to do almost cycle by cycle, and that's the problem, I think. So I'm somehow optimistic, but I feel that some problems that we really will benefit from this, the problems that will most benefit from this are the problems I think we'll learn a lot because we don't need to model 20 million cycles to learn what is the interplay between corrosion and fatigue and things like this. But whether someone will use it as an engineer for full scale design, maybe we're not yet there. Yeah. Again, high performance computing, people implementing these things in GPUs. I guess there's a million things one can do from a computational mechanics perspective. This is some of the things that we tried. Yeah.
So this is a question regarding the degradation function for heat. Now, when we use this, does it mean that we don't have to use the damage functions for the plasticity? Because we we are degrading stiffness in the fatigue equations, but if you were to go back before fatigue, before phase field, people would model fatigue using degradation functions for the material properties, right? To capture. So do we merge them together, or is it like if you use the degradation in the fatigue, we don't have to worry about Chabot kind of models?
So far I've only talking about linear elasticity because we're dealing with very high cycle fatigue or small scale yielding. I have some slides on plasticity. That's an even more tricky question. What do you do there? For the time being, we seem to be able to get good agreement with experiments. We've done mostly low cycle fatigue, plasticity, and so on. We do have nonlinear, so you need a proper constitutive model, Chabot style, so nonlinear kinematic hardening, nonlinear isotropic hardening, and so on. But once you incorporate that, then you have a fatigue degradation function, and that seems to be enough. So you do see the kind of cyclic behavior that you expect. You do see the drop in SN curves and so on. And we have now, I don't think I have slides for that, but I have a postdoc working on a model where we can see the change in shape of the SN curve. So it seems to be enough just having a proper constitutive behavior and then the degradation function based on this. So we're not coupling those in a way. It seems to be enough with this, yes.
But just having the degradation function for the phase field
Yeah.
should be sufficient, right? Why do we still need the Chabot kind of models for the constitutive model? Because you're already kind of saying...
You're saying even for the constitutive model, you say it's all embedded into it's all embedded into the degradation function.
Yeah.
Yeah, to a certain extent it's true. But it's a bit, for example, if you think of an SN curve, when you are accumulating cycles in the lower regime, everything is quite elastic. But then you need to have a model that somehow captures, I mean, I guess you could enrich your model to capture that when you get into plastic deformation, and then you're going to accumulate damage in a different way because you're going to have some hysteresis effects and you're going to have a different behavior. So I guess you could either incorporate I think the reason why we decided to incorporate this kind of nonlinear kinematic, so enrich the constitutive model as opposed to the phase field degradation function, was that we felt that in this way we will be more linked to the existing knowledge. So we know what is the back stress, what is strain hardening exponent. So we could, again, go to a table and pick parameters as opposed to enriching a function. But I guess you could do it. Why not? Yeah, it's a good. And probably, now that we discuss computational mechanics, it will probably much more I would say robust and efficient, because then you probably can jump things and you don't have to resolve these full cycles with all the kinematic hardening and so on. So that's not a bad idea. Yeah, and you can probably even compare them both and derive the enriched degradation functions with that. That's definitely a good idea. Yeah.
If we can reduce the convergence criteria,
maybe, yeah. We haven't done that because, well, you never know. When you start playing with convergence criteria, sometimes it's good, sometimes it's bad, sometimes you deviate from the real solution, and then you struggle to recover it back, and it's worse for convergence. Yeah, I guess one can play with those things. I don't expect big gains on that front. Yeah. And I think what was interesting of these models is that it's a paper that we have almost done. We haven't submitted it yet, but we were quite excited to show that we can predict the relationship for linear elastic materials. For plastic materials, there's other things happening. But for linear elastic materials, we can go actually from SN curves to Paris law. And this is something that has not done before. So these two stages of fatigue are treated independently. One is Paris law, and the other one is SN curve. I mean, you could think of both must be connected because both tell you how a material degrades when you have cyclic loading. But they had not been connected, but we can see that this is the case with our model. So you can see that we run simulations for different values of this N coefficient, and we get this type of slopes, and we get that different slopes when we run the Paris law. So somehow there's a relationship between the slope of the SN curve and the slope of the Paris law. And we can show that this is not only qualitative, but this is also quantitative. And we have shown also theoretically, we can do some calculations, some integrations, and you can show that if by considering some sort of damage mechanics approach, you can determine that the C value of the Paris law and the M value of the Paris law, they are related to the SN curve. So the M is related to is the inverse of this slope of the Paris curve, and the C is related to this fracture per Cezanne that depends on the fracture toughness and the M. And here you can see the comparison of the model with experiments on PMMA. So I think this is quite an important result because basically we're showing that for the first time that there is a direct link Paris came with this equation, but he didn't connect it to anything. It was just some 2 parameters that he fitted to the data and fitted very nicely. We showed that here there's a relationship, we showed both analytically and with phase field between those parameters, for linear elastic materials again, between those parameters and the descent curve. And we can show it for both experiments and theoretically that this is the case. So this is quite important because it means that ideally with phase field now, at least for these linear elastic materials, okay, we haven't cracked all the problem. We still have some parameters that we don't fully understand. But now we have this alpha 0, we have the n, and the n we can relate to the Paris law behavior. But more important, we only need to run one experiment, either descent curve experiment, which requires multiple ones, or a Paris law, and we can go from one to the other. And this is somehow important in the same way that this kind of transition flow, strength versus toughness behavior was important. It told me that phase field will tell me the right answer if you go from little cracks to big cracks. So here it tells me that if I go for a case where I have a small crack or a very large crack, stage 1 and stage 2, phase field will cover all cases.
Like you talked about that either I have to do one experiment for get descent curve, and from that I'll get the Paris curve, or I'll do the Paris curve and I'll get the descent curve.
Correct.
So, like, how do you implement R ratio experimentally in those cases, especially in case of Paris law?
How do you account for the R ratio?
Yes.
Yeah, so the model has an R ratio component. So the model has this R ratio component, and this R ratio component becomes more significant in the case of an descent curve, while it becomes less significant in the case of the Paris law, because it's more toughness dominated versus strength dominated failure. So it seems to, we don't have extensive validation, so it's very difficult to find data in the literature for, it has to be linear elastic materials. So linear elastic materials where, like PMMA, where they do descent curves at different R ratios and Paris law at different R ratios and so on. But so far it seems to be working okay. Again, for linear elastic materials, in elastoplastic, high regions of the descent curve, you have a change in behavior and there's other things happening. So again, very much ongoing work. We haven't even submitted this paper yet, but I think that it's exciting in the sense that we finally understand a little bit of what's underlying this kind of Paris law, which was very empirically driven, and this kind of descent curve behavior, this kind of Baskin's law, which is also very empirically driven. And the idea that you can go from one test and predict the other one, that's I think also quite powerful. So I'm excited about this. It's still ongoing work. There's things to polish, but I'm excited in the direction that it's going. And then another important result is this KT diagram, or Kitawa-Takasaki diagram. This is something that fatigue people use all the time. So it's a little bit the same idea of the transition flow size. So this is the strength versus the crack size. So this is the static result. Remember, you have the strength-dominated failures versus the fracture-dominated failures. And then the fatigue people use quite a lot the endurance one, so they have an endurance limit here. And then they basically build these KT diagrams for multiple cycles. So they do experiments, and they say, oh, for X number of cycles, for this crack size, I got this failure, and so on and so forth. And that allows them to tell them what is the transition flow size, right? How the transition flow size have changed, so they can compare that with their inspections. So we can see that we can recover that with phase field. So with phase field, we can run those simulations. We can capture nicely what happens in the static case. We can capture what happens in the endurance limit case, and then we can capture what happens in between. And again, I think this is quite powerful because we could tell engineers, what is the threshold, or what is the crack size, the critical crack size they need to focus if their application is going to be exposed to this number of cycles. So again, ongoing work, but recovering naturally the model, critical information from fatigue. And then I think we can probably do a break now, a 5-minute break. We also did experiments when we're looking at crack deflection. So these are, again, polystyrene samples. And you can see these are the dashed line of the experiments. So we run our phase field fatigue simulations. They basically change where you start your crack. So these are experiments where the distance between the crack and the circle was changed. And you can see that more or less, the computation seems to be in good agreement with experiments. You see the crack paths, there's small differences here and there, but the crack trajectory seems to be in good agreement with experiments. Okay, let's do a break now before I enter into elastoplasticity. So 3 past 10 or 4 past 10, we start again, 5-minute break? Okay. Any questions now before the break? Okay, we'll take the break.
24 number slide. This AYW, you are taking multiple cases, right?
Yes, changing the crack size.
Or we can do like that, like we know already the crack will propagate. So we have one geometry where there is a fixed A. So once the crack will propagate, automatically the A will change. Accordingly, the sigma will also be there. We have a sigma also, and particularly the crack
So
propagate.
you're saying instead of running multiple simulations,
With the
you
similar-
just take the same simulation and see how it grows with the number of cycles. I mean, it depends, because when you do fatigue crack growth, so you are damaging what is ahead of your crack. So it would be different if you had a, so it might not be a bad approximation, but you are cycling and you're already damaging this zone here. So it will be slightly different from the case where you start with a crack like this and this is undamaged. So it could be a bit of an effect, maybe it's not a strong effect. You're right, it could be interesting to test that. Yeah.
Sir, can you go to slide 25? Yes, sir. Sir, there is one hole beside the crack, and you can see that the crack is moving towards the hole.
Yeah.
Yeah. Sir, so similar experiments we were doing, we had two holes at equal distance.
So the crack, okay, like this.
At equal distance from the crack.
Did the crack always go to one of the holes? Or?
Yes. Sir, why is that?
And how will you run your experiment? Is it fully symmetric, or you are holding the at the
It's
bottom
a 4-point bending test.
4-point bending? And
So it should go straight, ideally.
I think the crack will see the hole. Depends on the distance of the hole. But the question is, why would it see one hole and not the other? Particularly when it's 4-point bending, which is fully symmetric. Interesting. I guess that could be microstructure or something. But if you do many experiments and they always follow the same hole, that's. But you could run the simulation with faces very quickly. It would be interesting too.
I was doing the experiment, I did not run the simulation. I'll show you. Sir, 1 second.
Sure.
Because ideally, if you think, then it should follow a straight path. Because loading is symmetric.
Yeah.
But always it is moving towards one hole.
Yeah. I think if the holes are sufficiently close, it will see one of them. But it's true that the stress state will be such that in theory it should go straight. But it's true that any minimal disruptions, some sort of microstructural phenomena will, you could try randomizing a little bit, do the simulation, randomize a little bit the material properties, and see how much you need to randomize properties for the crack to go to a hole versus going straight. So I think if you run the homogeneous simulation, you should be able to see the crack going straight.
I have not run the simulation yet. I'll do that.
Yeah, it will be interesting.
Not able to find that, but I have some other video. So in this case, I had the crack through the hole.
Mm-hmm.
But in this case also it was symmetric.
Yeah.
So we were doing this in photoelasticity. It will, in this case, it will follow a straight path. But when the crack tip is between the holes, it will move towards.
Yeah, interesting. Yeah, they will be interesting to. I mean, I could imagine this happening, because it's true that ideally it will go straight, but if you have some sort of heterogeneity, materials are never completely homogeneous, so it will be interesting to do the simulation. I would imagine that you will see the crack going straight, and then you will just randomize a little bit the material properties, and I think you have to see how much you need to randomize them for the crack to follow the hole.
Not a very simulation kind of. So can you help me?
But it's very easy. It's very easy. You should try.
Help me in the simulation?
Sure. If you have access to console, it'll tell you one
Sir,
morning.
Can I get your WhatsApp number?
I don't use much WhatsApp for professional purposes, but if you email me, I'll be able to.
Sir, can I get your email?
Yeah, Google my name and you'll find it online. It's
I'll
easy.
mail you the
Yeah,
images.
no problem. But if you have access to console, it'll be very easy, even with Abacus. It's not too
Actually, we're
complicated.
writing a paper on this.
Okay.
So, but I've not done the simulation work. So can we co-author that?
Yeah, I normally only get engaged in papers when I do them from the beginning. I'm big involved, but I'm happy to help you without having to be a co-author. No problem.
Simulation part.
I can give you some advice on the simulation. No problem. Okay. I think that we can continue. So everything so far has been linear elasticity. Of course, plasticity does play a role in metals. It doesn't play that big of a role in Paris law behavior. There, things are very small scale yielding, so the plastic behavior is very localized at the crack tip. So you can do the test. You can run a simulation with different strain hardening exponents, for example, and you will see almost no effect in Paris law kind of regime. But it does play an effect in other situations, of course. So what we did here was to extend the constitutive model to account for nonlinear kinematic and isotropic hardening behavior. You can see that it reproduces kind of the cyclic response that you expect from metals. This is for some steels. And you can see that the model seems to agree with what we see in terms of the SN curves, in this case, total strain amplitude is low cycle fatigue. Yeah, I mean, here again, you're seeing this. It's basically, I guess the takeaway is that you can combine these phase field models with any choice of constitutive model that you feel you can incorporate here. Of course, the more things you add into the model, the more you need to think about things and the more choices you have to make. So for example, here, we have this alpha that you accumulate. So you accumulate the elastic strain intensity again, the elastic plus plastic. We normally take this approach where we assume that only a percentage of the plastic work is stored. But when you're talking about fatigue, for example, a lot of the community that do crystal plasticity and so on, they could typically consider the stored plastic energy only because they say it dominates completely the behavior ahead of a crack. So the picture becomes a bit much more complicated, and there's some choices one has to make. So I mean, again, very much an ongoing discussion. There's nothing consensual yet, but I just wanted to show you that you can calculate this isotropic nonlinear kinematic behavior, and you can incorporate those things. And you can do that again in not only small scale samples but also large scale samples. You see a pipeline here where we did this sort of fatigue, and you can see the propagation of cracks and so on. Okay, the last item that I want to cover until the break at past is related to fatigue and the impact of surface roughness. So we were just precisely talking yesterday, visiting some of the labs here and talking with one of the academics here. We're explaining, how much they're interested in the impact of surface roughness on fatigue life. This is a well-known effect. We know that surface roughness has a significant impact on fatigue life. So people are quite worried about that. Normally, this could be due to, there's a number of reasons why you may get a rough surface. One of them is your manufacturing method, and this has become a very hot topic due to additive manufacturing. But the other one is corrosion and problems like this. If you have some sort of aggressive environment, you get a rough surface, and then you get a degradation in your fatigue life. And you're not sure whether the degradation is due to the effect of the rough surface, whether the effect of the combination of corrosion and fatigue, and so on and so forth. So there's significant interest in trying to quantify this effect of the roughness of the surface, particularly these days mostly to additive manufacturing. We know that we get a rougher surface in additive manufacturing. We know this is going to damage our fatigue life. How much is going to damage our fatigue life? How much do I need to improve? What kind of treatments I need to do? And this is something that is well known. So for many, many years, people have been working on, and this is, by the way, work, I'll talk about work that my postdoc Sara Jimenez Alfaro has done. The paper is currently under review. But basically, what people do in the community, this is the fact that your fatigue life degrades significantly with roughness is something that people know since, I guess, in the 70s or something like this, so quite a long time ago. And people came up with basically what they call a surface factor, this KS, surface factor. This is sort of a correction factor that tells you if you have a polished sample, a smooth sample, and this is the endurance limit or the fatigue life, the fatigue strength at 1,000,000 cycles, then the endurance limit, this is what you're interested in, right? So you say, I have a material X, I'm working with, I don't know, titanium alloy, stainless steel, I'm working with a carbon steel, I know what is the fatigue life of my material at 1,000,000 cycles. Now I know that I'm going to apply some sort of manufacturing methods, it's going to be exposed to a corrosive environment, something is going to change the surface, so you want to know your new fatigue life, and you do that through this definition of this correction or surface factor. So this is an important parameter. Just to emphasize this point, in order to quantify what is the effect of roughness on the fatigue life, we define the surface correction factor, that is the ratio between the fatigue life, the fatigue strength at 1,000,000 cycles, so the endurance limit, of the rough sample versus the polished sample of the same material. And you can see here the surface factor for a given material as a function of the tensile strength. We know that there's a sensitivity to tensile strength, and as a function of the surface finish. you can see, a factor of 1 means they are equal. The effect of roughness goes away. So that may happen if your surface finish is perfect. But the moment you have some sort of surface finish issues, you can see that this is dropping almost to 0.5. This is what people tend to observe. The down limit is that the surface factor, the fatigue life, can be reduced by half if you have a very rough surface. This is what people are seeing in experiments. You can also see it here as a function of tensile strength, surface factor, different as forge, hot roll, and so on. Again, different conditions. Okay, so the idea is, okay, can we use phase field to naturally predict this surface factor? Because the way people predict the surface factor is by running many experiments. So you run a lot of experiments on smooth samples, then you run experiments on, if you're interested in a particular manufacturing technique, imagine 3D printing, right? You 3D print your sample, you see a certain roughness, you do many experiments to get your surface correction factor, and then if you change your 3D printing parameters, you need to do again many experiments to predict your surface correction factor. So is there any way that we can use phase field to predict what is the surface correction factor? So the idea is that basically develop a new tool where we can some sort of combine these phase field fatigue models that we discussed before. We use the model of my student Ligesa Glamar, and a stochastic model that allows us to build finite element models that have roughness. And then with those tools, we aim to answer the question that how can we estimate how much the fatigue life is reduced for a given surface roughness and material properties. And you see here some S and curves. So first of all, the fatigue model, we take the one of Ligesa, the one that I showed you before, and with this model, we seem to be able to fit quite nicely the experiments. So the fatigue model, this is on the smooth samples. The fatigue model seems to be working okay. Now the question is, what do you do with the roughness? And you need some sort of a statistical model. So you need to develop a new finite element tool that allows you to capture this. So people normally quantify roughness using a couple of parameters, typically 2. So there's this RQ, which can be related to another one called RA, and this correlation length. These are the 2 parameters. So this will be the case, for example, of a perfect roughness. So you have basically a quantity set. Set is the normal to the surface, so it will give you how much of the roughness of the surface you have. So you have some sort of, this was you make a bit of a white noise. So some people have been working with these things in image techniques, in optics and so on, to come up with kind of rough surfaces. So this is a rough surface, then you can come up with, this is a smooth surface, then the blue line is a rough surface. And this rough surface is characterized by, the distance to each of those points. And this is described by this RQ, which is the root mean square surface roughness, and this correlation length. So I'm not going to get too much into the details, but basically you have 2 parameters that characterize your roughness. And this is another one, and again, all of these are characterized by those 2 parameters. So the way we work normally in this framework is that first we build a mesh, assuming a polished sample. Then we define the surface roughness to these 2 parameters, RA and L correlation. These 2 parameters can uniquely define, the roughness of your mesh. Then you obtain this R matrix that you calculate here, so this equation here. You start iterating your sample. So for a given applied, so this is a stochastic process, right? Because as you can imagine, these 2 parameters can characterize a surface, but it's not unique. You need to run multiple simulations to get some sort of the same average roughness. So what we do is we look at the experimental roughness that we want to reproduce. We characterize with 2 parameters, and then you can get some sort of the same average roughness, but you can get different behavior. So what we do is we create one case study, we run it, we apply the load, we calculate with phase field what is the number of cycles to failure. We see is our calculation statistically representative, or if we do an equivalent rough surface, but it's slightly different because the surfaces are never identical, do we get the same result or not? And if you do enough calculations, you eventually converge to a single value. So then when you compare that, you can calculate something that is the margin of error, and you need to do a number of iterations. We realize that we need to do at least 30 simulations per surface, otherwise we get scatter in the results. Because of course the cracking process might be governed by the biggest defect that you have in a way. So you need to do a number of calculations. You calculate the margin of error. You again produce this white noise variable. You again build the mesh. You again compute the fracture, and then you estimate again the fracture surface, and so on and so forth. So let me show you how it works. I think it's going to be a bit more clear when I show you some results. So this is the finite element model. First you start with a smooth surface, then we say, okay, we have an algorithm that says, now we're going to deal with, I remind you that I have 2 parameters that tell me what is the size of the surface, RA and L correlation. So for 2 different sizes, you automatically generate this. And you can imagine that the computational cost is going to grow because you need to resolve your roughness and your phase field length scale. So your element size, H, has to be 5 times smaller than both your phase field and your kind of correlation length that characterizes your roughness. So you can see here that if your correlation length is 10 microns, we're going towards 100,000s of elements. So it changes quite significantly. But anyway, you enforce this, and it is what it is. It's the price that you need to pay. So this is a correlation length of 10.8, and then you basically run these calculations. You generate this mesh, and now when you run the calculations, you get something like this. Eventually, the cracks start growing from those defects of the surface, from the stress concentrators, and eventually, you get an unstable crack growth and the failure of the sample. So that's what gives you the number of cycles to failure. So this is the process. But every time you generate a mesh like this, there's going to be some sort of a stochastic. You're generating some noise. So every mesh that you generate is going to be slightly different. So you need to run enough number of calculations to get a statistically representative result. And then so you get a bit of a scatter. So then once you do that, you can compare with experiments. So let me see. Yeah, you can compare with experiments. So this is, I forgot to include an image, but you can see that when you run more than 30 calculations, more or less, you start seeing your margin of error decrease. So you start seeing how the number of surfaces that you tested for those 2 variables start seeing enough. But basically, this is what you get. So this is the surface factor. The symbols are experiments, and this is the average surface roughness. In those experiments, with the exception of this set of experiments, we didn't know the correlation length. So we know this average surface roughness, but the people doing the experiments, they didn't know the correlation length. They didn't provide that value. So we had to basically take a range of parameters between the values that are typically reported in the literature, which means that we get a bit of variation in our calculations. This is why we get these blue bars. Nevertheless, I think that we get much less variation here, which is the case where we know the correlation length. We get a bit of variation due to the scatter that comes into the model, but it seems to be okay. And you can see, the trend seems to be in the good direction. We seem to capture very nicely what we see in the experiment. So again, if we knew the correlation length, things would improve, but this seems to be a trend in the good direction. The model seems to be working quite well. And then what is interesting is that we can come up with these maps, and this is the key result. We can produce this kind of surface factor maps, which tells us what is the surface factor, so how much we degrade our fatigue life with these 2 quantities that characterize your roughness. So what you see here, first of all, of course you see what you expect in a way that, the rougher your surface, the more you degrade your toughness. So here, you're degrading more your toughness. You can see that the smallest values, we are taking values of average surface roughness and correlation that are representative of what you get out of manufacturing processes, pitting corrosion. And you can see that the smallest number that we get of surface roughness, of surface factor, is around 0.5, which is what is reported in the literature. The experimental literature typically reports a 50% reduction in the worst cases. So this is what we also get. But we can also test that it seems to be in good agreement with experimental data out there. So when we do 3D printing, laser powder bed fusion of 316 stainless steel with an RA, there's some data from the literature with RA between 18 and 21 microns, we get a reduction factor of 0.77. So that is roughly for this case. So if you go here, somewhere here, that is roughly 10% deviation from our prediction. So that's, I think, quite good. And then also for corroded samples, in this case the material, so this is for a given material with a given strength. The strength plays a big role on this. But with a material with a different strength, still for corroded samples that had pits of 50 microns, the reduction in fatigue life was roughly from 390 to 200 megapascal, which is 12% of our prediction. So despite the fact that we're modeling a different material with a different strength, we will be much closer if we had the right strength. We seem to be quite close. So I think that's an important result. Of course, it takes a lot of calculations to build a map like this, because we run at least 30 simulations per combination of surface factors, because we get a statistically representative result, and we are building, we're running dozens or hundreds of simulations to build this map. But I think this is quite interesting, the fact that you can use a computational tool for the first time to be able to predict this kind of surface behavior. So just to emphasize the point, the idea here is that there's an effect of the surface roughness on the endurance of the material. This effect is quite strong. We want to capture that effect using phase field fatigue. We can do it. For that, we use this model that we are showing here, the one of Aliguesa, this one here. And the way we capture this is by, oops, sorry for that, I went too fast. The way we capture is by running some sort of a statistical analysis where we have a way of taking from the optics community, where we generate a surface roughness as a function of 2 parameters. We have some white noise in there, and therefore we need to run a statistical analysis that the predictions of phase field might be, I mean, this is deterministic in a way, but the predictions of phase field might depend on your surface roughness, of course, even for 2 parameters that you've chosen. So we run enough calculations. We calculate the margin of error. We make sure that our margin of error is within a certain percentage, and then we can determine the fatigue life for each of those calculations. And as you can see here, the prediction with experiments, even though there's a bit of a scatter because of this running multiple simulations, and because here we didn't know from the experiments which was the correlation length, we seem to be capturing quite well the data. And importantly, we can build these sort of maps where we can tell what is the degradation in fatigue life that you're going to get. Again, the surface factor is endurance, so fatigue life at 1,000,000 cycles of a smooth sample versus a rough sample. So you can see, if the surface roughness is very small, this corner, bottom right corner, then of course you get the same result as a smooth sample. The opposite corner, you get half reduction in fatigue life. This is what we see in the experiments. The worst case scenarios is typically a 50% reduction. And then we can also see, when we sample things from the literature, so for an additive manufacturing component, we have seen experiments that for this surface factor, average surface roughness, we get this kind of reduction, and this seems to be within 10% of our map, and the same for pitting. So again, this is quite important because, as you can imagine, for example, in offshore wind turbines, in fact, the project that Sarah is funded for is based on offshore wind turbines, so they have a lot of pitting corrosion, and they want to figure out from that pitting corrosion what will be the impact on their fatigue lives. So you can run the simulations, and you can predict what will be the impact on the fatigue life. Okay, I think that's all for phase field fatigue. Any questions? Yeah.
So, it's a bit puzzling to me why the fatigue degradation function is degrading the fracture toughness instead of the stored energy or the elastic energy. When you started phase field, you were degrading the stored energy, so the phi was on the right side, right? Where it is phi was used degrading the side.
So let me go back here. I mean, it's a choice, maybe just here. So it's a choice. So we have a driving force, and you have a fracture resistance, toughness, and accumulation of your driving force for fracture, stored energy. Some people have argued in the phase field fatigue community that it's the same, a little bit the same for the phase field ductile fracture community. So there's been 2 approaches. Some people say, I want to enhance my driving force. I want to maybe increase this with the number of cycles, or I'm going to degrade my fracture resistance. I tend to like, and I did the same for hydrogen, I tend to like to degrade my fracture resistance because I see it as a more physical, maybe it's a bit philosophical, but a bit more physical in the sense that this is what I think is happening in reality. Hydrogen is degrading my bonding strength, fatigue, this kind of accumulation of cycles is degrading a little bit my resistance to fracture. But I guess you could think of being it as well a driving force. You could say, I have a static driving force, and now I have something that is enhancing my driving force, or something along those lines. Yeah.
It's a little bit inconsistent if you just take phase field fracture for brittle materials,
Mm-hmm.
right? So even there, you're still saying once a crack is propagating, your fracture toughness of the material is actually degrading. So you could actually have the 1 minus P.
But you don't degrade your fracture toughness, right? Your fracture toughness is a constant. You degrade your balance of linear momentum, right? So you have the and then here you have a phase field degradation. So you are phase field fatigue continues to degrade this. So damage is the same. So I guess damage we can think of micro cracking. The degree of micro cracking, we don't know whether it came from fatigue, whether it came from fracture. It's going to just degrade my stiffness no matter what. And then how quickly it is to generate that damage will be dependent on your number of cycles. How easy it is to generate that damage, those micro cracks will depend on your number of cycles.
So the left-hand side of that equation that we have with the F alpha on the screen.
Sorry.
So the fatigue degradation function is multiplied with GC.
Yeah. So and this is going down.
So that's going down. So in a way, you're saying that the effective fracture toughness of the material is going down.
Yes, with the cumulative number of cycles. So it's easier to grow a crack if you have. Yeah.
But the same argument can be made even for a brittle material. Once the crack starts, of course, it goes completely, but the fracture toughness goes down. So 1 minus psi.
But does it really go down, the fracture toughness of brittle material, in the sense that it's a material property that remains the same? It's just your driving force goes up, right? If you have a larger crack, your stress intensity factor will go up, but your toughness will remain the same. It will be easier to propagate a crack just because you have a larger crack or you have a larger applied load.
So there are folks who use the fatigue degradation not for the GC but for the stored the driving force.
Yes, so I guess maybe it's a philosophical point of view. I do prefer this approach, but there have been various cases. I think the very first paper from the UT Austin group, what they did was a bit more empirical, I would argue, that what they did was they had this viscosity coefficient, and they changed the viscosity coefficient to reproduce Paris law. But then there were other groups, also in the facial fracture, ductal fracture community, where they have some sort of enhancement of the driving force. So they say with the number of cycles, I'm not only storing this energy, I'm storing a bit more, something more. And therefore, the toughness remains the same, but cracking becomes more easy because this guy is a bit bigger because I accumulated during cycles and so on. Yeah, I still kind of prefer, but it can be a bit of a personal viewpoint of thing. I still prefer to think that my accumulation of cycles is degrading my fracture energy, but I saw a very good talk by Roberto Alessi at Compla some years ago where he made an argument for both cases, and it sounded convincing, I guess. You could always do it in both ways. Yeah.
So is it okay to then think that you're actually the fracture toughness of the material is degrading because of fatigue?
I think so, and I think that's consistent with what you, for example, think of this KT diagrams that the fatigue community uses quite a lot. So these KT diagrams, they'll tell you, the transition flow size as a function of number of cycles, and the transition flow size is basically, how it changes between the failure, I guess failure stress versus crack size as a function of strength, which is not going to change that much. Oh, it's going to change with fatigue, of course, but also about fracture energy. And I think it makes sense that we know that the transition flow size goes in this, so this is the static case, we know it goes in this direction, so the experiments show it all the time. And for it to go in this direction, I guess, it could be this guy could remain the same and this could just go down, but then it will go somehow in this direction, right? So in order to go in this direction, both curves need to go down. So I think, to me, it's the most sensible approach. It's a bit philosophical, and probably you can get the same kind of qualitative results whether you pick one or the other, and this seems to be what we see in the community. But I do like the idea that, and I don't know if you will be able to recover this type of behavior, for example, with the driving force. Maybe you do, I don't know. I haven't run that calculation. Yeah. Thanks.
What are the length scale parameter, like GC is degrading, so maybe that L is also a material property that.
Yes, so if you remember the equation for the relationship between the strength and the sigma, the strength, it was something along those lines. So you have E, you have GC here, and then you have L, and then some sort of factor, whatever constant there. So it is true that by degrading the toughness, you are already degrading the strength. That's why you see this drop in the KT diagram. That being said, is this the way the strength should be degraded? It's a little bit similar to the hydrogen. In the hydrogen problem, it's the same thing. We degrade this guy, and automatically this is degrading the strength. And we see in experiments this type of thing. So the qualitative trend is the same. But is this, the right relationship? Should we do something else here? Should we change also a little bit the length scale so that, the factor is the right one? Yeah, difficult to tell. Yeah. But it's a good question. Yeah. So far we're assuming, this will get us far. And I mean, it seems to, we can capture SN curves which are strength dominated and Paris law with the same scheme. So things seem to be going in the right direction, but it is, an open question. I guess one could refine the details further. Yeah. Okay, it's 11:30, so we can take a coffee break until 11 now.